In this video, we will study Euler Lagrange equation. Euler Lagrange equation. We'll study some of the applications of Euler Lagrange equation. So if you remember, Euler Lagrange equation was del f by del y minus d by dx of del f by del y prime is equal to 0, where f was a function of x, y, and y prime. Okay, if you don't remember this, go back and watch my previous video. In the previous video, we have derived the Euler Lagrange equation. Okay, so today we will do the several applications. The first application is called shortest distance between two points. Okay, now let's say we are on a plane, and there are two points on the plane. The first point is x1, y1. The second point is x2, y2. And we are interested in finding out what is the curve that joins these 2 points such that the length of the curve is minimum. So let's say we want to go from x1, y1 to x2, y2, and we want to traverse the least amount of distance. So we want to find out the path which has the least distance from x1, y1 to x2, y2. Okay, typically what we will do for this is, if you want to calculate the distance between any 2 points, typically what we will do is we can divide the whole path into smaller lengths. Okay, and then we take the measurement of each one of these lengths, and then we can add them up, and then we will find which is the curve for which this length which we have added through over the curve is the minimum. Okay, so the typical process is this process of summing over the length is essentially an integral. So we can write this integral as integral of some small length ds, where ds is the length of a small element of this curve, and then we integrate this ds from point 1 to point 2. Okay, if we do this, we can find out the length of the whole curve, and then our goal is to minimize this length. But the minimization of this integral can essentially be given by the Euler Lagrange equation. Okay, so let's first find out what would be this integral. So in this case, we have a small distance ds, right? So what I'm going to do now is I'm going to blow this small part. I'm going to make it large. Okay, so let's say we are still on some xy axis, but now instead of the whole curve, I am drawing a small part of the curve, which is this length ds. Okay, now if we are taking a very small part, infinitesimally small part of the curve, then this length is almost like a straight line, right? If you take a really small part, then this curve will be almost like a straight line, and then we can look at this curve as a part of a right angled triangle whose two sides are dx and dy, and the third side is this length element ds. Okay, if that is true, then in this limit, ds is simply square root of dx squared plus dy squared. That is through Pythagoras theorem. So we can write this integral as 1 to 2 square root of dx squared plus dy squared. Okay, now what we're going to do is we are going to take dx common from both these terms, which will give us a 1 plus dy over dx whole squared. Oh, so now what is dy over dx? Dy over dx is simply y prime So we have this 1 plus y prime squared integral. So this integral I, which was the length of the curve from point 1 to point 2, is I equals integral 1 to 2 dx 1 plus y prime square. Now this is very similar to the integral that we minimized or extremized to get our Euler Lagrange equation. The only difference is that instead of the function f that we had earlier, this f function x, y, y prime that we extremized to get our Euler Lagrange equation, in place of f we have 1 plus y prime square. So simply we can write as f of x, y, y prime is square root of 1 plus y prime square. Okay, so in this case, the function f of x, y, y prime is only a function of y prime. It is not a function of x or y, which in some sense will make our life much more easier. So now that we know what the function f is, all we need to do is we need to apply this f in our Euler Lagrange equation, and we will get the differential equation for y, which we will solve. So let's do that. So Euler Lagrange equation is del f by del y minus d by dx of del f by del y prime. This can also be written, sometimes it's written like del f by del y. Let me be clear. Del f by del y is d by dx of del f by del y prime. It's the same thing. I've just in place of this negative sign, I have taken this on the right hand side to write it as equal sign. Now let's calculate these terms. What is del f by del y? Now we know that f is not a function of y in this case, so del f by del y is simply equal to 0. Also we can calculate del f by del y prime. Del f by del y prime would be del by del y prime of square root of 1 plus y prime square. Okay, this is simple differentiation. This is the differentiation of a quantity whose power is 1 by 2. Okay, so if the power is 1 by 2, then we can simply write that 1 over 2, the quantity in the bracket, so this would be 1 plus y prime square. It goes in the denominator, and then we have to differentiate with respect to y prime whatever is under the square root. So under the square root we have 2 y prime. So the derivative is going to be equal to y prime over 1 plus y prime squared under root. Okay, that's the derivative del f by del y prime. Now let's plug these values back in our Euler Lagrange equation. So now our Euler Lagrange equation becomes, the left hand side is simply equal to 0, and the right hand side becomes d by dx of y prime by 1 plus y prime squared. Now we see that the full derivative of this function is equal to 0. What does that mean? That means that this function must be a constant. So y prime by 1 plus y prime square root should be a constant. Okay? To simplify this, what we are going to do is we are going to take the square of the whole thing, which will give us y prime square by 1 plus y prime square equals c square. Now what we can do is we can do some simple algebra, which will give us y prime squared equals c square 1 plus y prime squared. Okay, now that's all I have done is I have taken this denominator to the right hand side. Now what we want to do is we want to group the terms which has y prime on the same side. So let's write it as y prime c square y prime squared. Okay, so let's bring all the terms which has y prime on the left hand side. So we'll get a y prime squared minus c square y prime squared equals c squared. Let's take y prime squared as a common. So we'll get 1 minus c squared equals c squared. Finally, let's write y prime squared as c squared by 1 minus c squared. So y prime squared is now some constant. Okay, we can further simplify this by writing y prime. We can write y prime as the square root of c square by 1 minus c square. Now c square by 1 minus c square square root, c was a constant, some arbitrary constant. So this quantity is also some constant. Let's just call this constant m. Okay, then we have dy by dx y prime or dy by dx equals m. Now this is a simple first order differential equation. We can solve this very easily. Let's do that. So dy becomes m dx. Let's integrate this. If we integrate this, we will get y equals mx plus some other constant. Let's call it p. Okay, so this is the functional form of y. So y as a function of x equals mx plus b. So this is the functional form of a curve that if you take this curve and you go from point 1 to point 2 on a plane. So point 1 to point 2 on a plane. If you go along this curve where y is defined as mx plus b, then that will give you the shortest length between the 2 points. Now you might already know this. This is simply a function of a straight line. So on a plane, the curve that joins 2 points and has the shortest length is the straight line. We already know this. So right now all we did was we used the Euler Lagrange method to find the shortest distance between 2 lines. Okay, we already know this. The reason we are doing this is that we can see how this approach of Euler Lagrange formulation is utilized to solve problems in calculus of variation and in Lagrangian mechanics. Okay, just to summarize, what we have done is we first make this integral. So our first goal is to get this integral, that integral which defines our problem. The problem was defined as find the shortest distance between 2 points. So we first assume that there is a curve that joins these 2 points. Then we integrated along this curve a small length element, because the sum of a length element integrated along the curve gives us the length of the curve. Now once we got the functional form of this integral, which was the length of the curve, we identified what was the function f of our Euler Lagrange method. And once we got that function f, then we simply plugged in the values in the Euler Lagrange equation. This is the Euler Lagrange equation. And then we did simple algebra and some simple differential equations to find out our solution y as a function of x. And in classical mechanics, or typically in calculus of variation, the goal is generally to find out y of x. Sometimes the goal is to stop here, to find out the differential equation. Once you know the differential equation, you can either solve it, and if you can't solve it, then you plug it into a computer and the computer can solve it. But generally the harder part is getting this differential equation, which is what we will do most of the time. Okay, let's do another application in the next video. Thanks.